This video, we're going to discuss a pretty typical type of question to encounter early in your calculus course. We have an equation here. Now this equation, because it doesn't have y isolated, it's not likely that it's a function. So for this relation, what we would like to determine is where its graph has horizontal tangent lines and vertical tangent lines. Now if you're ever doing a problem involving tangent lines, you need your derivative. Now if you think about this particular equation, you're not going to be able to take the derivative of this in the normal way. We do not have y isolated within this equation. A lot of the times I see people think, all right, well, I've got to solve this equation for y. There's not that efficient of a way to do that in a lot of instances. So what's probably a more viable option is to just take your derivative implicitly. So what that means is we're just going to take the derivative of both sides of the equation with respect to x. And we make an assumption when we do this. We assume that y is a function of x. So when I take the derivative of x times y squared, if y is a function of x, this is two functions of x multiplied together. So I'm going to have to use a product rule. The derivative of x is 1, and then there's the original second piece of the product, and then I'm adding on the original first piece of the product, and then I need the derivative of y squared. Well, if y is a function of x, what I'm going to need to use to take the derivative of y squared is a chain rule. So I'm going to multiply by the exponent, subtract 1 from the exponent, so 2 something to the first power. The something has to stay the same inner function, so 2y to the first for the beginning of our chain rule. And then I'm going to finish my chain rule by multiplying by the derivative of that inside function. And the derivative of y with respect to x is dy dx. I'm going to subtract off the derivative of 2 times y. And that is going to be 2 dy dx. And then don't forget about the derivative on the other side. I have the tendency to see people do the hard stuff correctly and then just get a little careless and forget to take the derivative on the other side of the equal sign, especially when it's as simple as it is here. Now from here, we want to do some algebra to try to isolate dy dx. So the pretty frequently used sequence of steps is to move anything that does not contain a dy dx. And this is the only term that does not contain dy dx. And keep in mind, terms are separated by addition and subtraction. So the parentheses that you see here, the parentheses that you see here, those were really just used to kind of help structure the product rule that I was carrying out. But this is one term, this is a second term, and then after this subtraction, we have a third term. So two of those three terms do contain dy dx. I'm going to leave those on the left side of the equal sign. This y squared term, I'm going to subtract from both sides so that I don't have any terms that are without dy dx on the left. And then what I can do is I can factor dy dx out as a common factor from those terms that remain on the left. And then to totally isolate dy dx, I'm just going to divide that right side of the equation by this quantity that we're left with after dy dx has been taken out as a common factor. We have our derivative. Next task, where do we have horizontal tangents? So if you think about horizontal tangent lines are going to have a slope of 0. A tangent line will have a slope of 0 if the derivative has a value of 0. This fraction is only ever going to take on a value of 0 if the top of the fraction is 0 while the bottom of the fraction is not 0. So I set the top of the fraction equal to 0. I get the solution y equals 0. Now, does y equals 0 also make the denominator 0? Because keep in mind, 0 divided by 0 is an indeterminate form. 0 going here in place of this y is going to make this piece go away. 0 divided by -2 is not 0 over 0. So the only location where my derivative equals 0 is where y is equal to 0. A lot of times I'll see people say, all right, well, I know I have a horizontal tangent line where y is equal to 0. What you don't yet know is you don't know if there's even a point on the curve where y is equal to 0. So what we're going to need to do in order to figure out where on the curve y is equal to 0, we're going to have to take that y that we just identified, and we're going to have to replace the y in the original relation with 0. When we do that, we get x times 0 squared, that's x times 0, that is 0. And then we get minus 2 times 0. 0 does not equal 2. What that tells me is that there's nowhere on the curve where y is equal to 0. I don't get a corresponding x to get returned when I plug 0 in for y. So that tells me that I have no horizontal tangents. So if we move on to vertical tangents, a vertical tangent line is going to have an undefined slope. And since it is a tangent line, we'd be looking to identify when the derivative is undefined. This derivative is going to be undefined when the denominator is 0. Now this equation is a bit different than the one that we saw in the horizontal half of the problem because you have both x and y in this equation. You will not be able to solve this for a numerical value for either x or y. But there's another condition that needs to be satisfied here. If you think about what we did in the secondary part of the horizontal part of the problem, which was ask, hey, where on the graph does y even equal 0? We can ask that question right now. We know we're looking for an ordered pair x comma y, and it has to be on this curve. So if this equation is true, our derivative is undefined. But if this equation is true, our point is actually on the curve. So both of these would need to be true simultaneously in order for us to have an undefined tangent somewhere on the curve. We treat this as a system of equations, and I'm going to solve this system by substitution. So I look at this top equation. I think it's a little nicer to solve for both x and y than this bottom one is for either of those variables. I'm going to choose to solve this equation for x. The reason why, I would rather substitute in place of a single x rather than in place of multiple y's and have to square one of those substitutions. So I'm going to solve this equation for x. I've done that right here. Add the 2, divide by 2, divide by y. Once I see that x is equal to 1 over y, I'm going to substitute that in place of this x. 1 over y times y squared. That will simplify to y as long as y doesn't end up being 0. That algebra is eligible to be done. So we'll double check that in a few seconds. Once I do simplify that to a y minus 2y is negative 1y, and then dividing both sides by negative 1 gives me a solution of negative 2 for y. Y does not equal 0, so this algebra back here was able to be done. Now that I know my y coordinate where this happens is negative 2, what's the corresponding x? Well, I can plug that in over here. 1 divided by negative 2 is negative 1/2. This tells us we have a vertical tangent on this graph at the x of negative 1/2 and the y of negative 2. You won't necessarily be able to build this graph very effectively on a graphing calculator, but if you do go to Desmos, you can graph this there. And the graph is not a function. It fails the vertical line test all over the place, which is why I've been trying to be careful and call this a relation throughout this discussion. You don't really see any location on this graph where we would have a horizontal tangent. The graph is leveling off way out here as x approaches infinity, but that kind of indicates a horizontal asymptote most likely rather than a horizontal tangent line. But if you look at this location right here, it does seem like we would have a vertical tangent line right at the x value of, pay attention to the scale on the x-axis, looks like we're dealing with half unit grid. So it looks like that is an x of negative 1/2, and the y clearly is negative 2.